All right, so it's a pleasure. Today we have Sebastián Franco, who will tell us about 4D crystal melting, Toric Calabi-Yau fourfolds, and brain brick models. Take it away.
Okay, so thank you everyone. Thank you, Julius, for the invitation to talk here. The Quiver Meeting is, of course, the seminar series that I like the most because of the friends and because of the topics. And today I wanted to talk about, some paper that I wrote recently, a couple of months ago, about some generalizations of the crystal melting models that we know based on dimer models to Toric Calabi-Yau fourfolds, how they are based on brain brick models. I'm very interested in the topic. I think there are many interesting things to do moving forward. The talk today will be about setting up the model. For those of you that are not so familiar with what the brain brick models are, it will be an introduction to that. And it will have a lot of hopefully nice pictures that you will enjoy, because sometimes visualizing these things is complicated. So the talk is going to be organized as follows. I will give you an introduction and a motivation of why I think it's interesting to be doing this right now, even though this was sitting in the drawer for a very, very long number of years. But we had to get moving at some point. I will tell you a brief introduction about brain brick models. I will tell you about the combinatorics of these brain brick models, at least the topics that are important for the talk. I will then introduce a crystal melting model for Toric Calabi-Yau fourfolds. The discussion will be quite general, but immediately after that, I will focus on the simplex example, which is C4, flat space. And I will show you how the crystal looks like, how to think about it, how to visualize it. The initial formulation of the model will be in terms of a quiver, and then I will move to formulation of the model in terms of the brain brick models. Okay, and I will explain how to do what to do there, and then I will emphasize how this model is general, or what are the directions that we would like to study in terms of generalization, more general geometries, more general brain configurations, and I will conclude with some future directions. So please stop me whenever you want. There are a lot of slides. So, there are this. So what is the motivation? Many years ago, we learned about these beautiful crystal melting models that capture the BPS spectrum of D-branes on Toric Calabi-Yau threefolds. They follow the very seminal work of all these people, and then Oguri and Yamasaki wrote a paper going step by step on explaining the model. And in these models, there are crystals, there are three-dimensional crystals. And an interesting fact is that the crystalline structure of the model is given by the brain tiling corresponding to the Toric Calabi-Yau threefold. I don't think that I have to explain what the brain tiling is for the audience, but there is some bipartite graph on a torus that captures both the geometry and the gauge theory of these branes probing that geometry. So here I show you not the dimer model on a torus, or the brain tiling on a torus. I show you the universal cover of the torus for the case of flat space, or SIS3. If you want, the corresponding gauge theory would be n equals to 4 super young mills. And you see here in red some edges. This is a perfect matching of this cover. And the way you think about this three-dimensional crystal, at least in this very simple case, is that you can think about replacing edges in the perfect matching by rhombi, and it immediately gives you an idea of this third dimension that you are looking at. Okay, so this perfect matching here is different from the perfect matching at the center. It differs from it by a flip of the edges that are in the perfect matching around the central hexagon, and that's why you have this box. And the third one is yet another one. And there are different ways of thinking about this third dimension. And of course, this was well known even before people thought about these crystal melting models. So, okay, so we are talking about this BPS spectrum of branes in Calabi-Yau threefolds. We are talking about crystal melting models that have to do with the brane tilings, which are the brane configurations that describe in a very efficient way the corresponding gauge theories, which are in 4 dimensions. But recently there has been a program, and we have been working on a program that is very similar to the one that led to the brane tilings, that was interested in thinking about efficient ways of understanding the gauge theories on D1 branes probing Toric Calabi-Yau fourfolds. These are generically 2-dimensional 0,2 theories. And the outcome of one of the main results of this program was the introduction of the so-called brane brick models, which are, if you want, the analogs of brane tilings for Calabi-Yau fourfolds. They're not I will explain them. They're not a straightforward generalization, but they're quite a similar generalization of brane tilings. So in a recent line of developments at the same time, I mean, these are 3-dimensional objects compared to the 2-dimensional brane tilings that underlie these Calabi-Yau 3 crystals. At the same time, Nekrasov has been working on the Magnificent 4 model that computes the index for D0 branes in the presence of D8 and anti-D8 branes in C4, and its variables are solid partitions. If you want, solid partitions are things that you make out of 4-dimensional boxes. So it's reminiscent to this picture here. And what we're going to do today, in part motivated by these conversions of recent developments, is just to take a first step, and I will tell you, I will define for you a crystal melting model that is based on the brane brick models. That describes, and of course, the correspondent has to be refined in the case of Calabi-Yau fourfolds, but let's say vaguely that it describes the BPS spectrum of D-branes on Toric Calabi-Yau fourfolds. So what is a brane brick model? It's a type 2A configuration that is dual to D1 branes over Toric Calabi-Yau 4 singularities. The configuration looks like this. Initially you have D1 branes probing some Calabi-Yau fourfold. You are interested in the gauge theory that appears here. That is a generically 2-dimensional 0,2, but might have additional supersymmetry in special cases. And the T-dual looks like this. You have some D4 branes, and some NS5 branes, which are spanning 2 dimensions, which are the dimensions in which the gauge theory lives. And then, the D4 brane is covering or stretching, the D4 branes are stretching along 3 internal dimensions, which are forming a torus. And the NS5 brane, which captures information about the geometry, is wrapped on a 4 real dimensional space or a complex surface in size D6 dimensions. The configuration is a point on the 8 and 9 directions, and rotations there are the U and R symmetry of the gauge theory. So what you can do is you can take, combine all these 6 coordinates, 2, 3, 4, 5, and 6, 7 into complex coordinates x, y, and z. We can think about 2, 4, and 6 as being the arguments of those complex coordinates. Okay, so what is sigma? Sigma is where all the information, all the non-trivial piece of the non-trivial physics happens. Well, sigma is given by the 0 locus of the Newton polynomial defined by the toric diagram. So you have a polynomial in which you have one coefficient for each of these terms. It's a complex coefficient. You set it to 0. Of course, you can rescale some of them away. The answer does depend on the coefficients. So very interestingly, for example, you can vary these coefficients and you can get dual theories related by triality and things like that. So it's a very nice setup. So what we have is most of what I will discuss happens in this 3-dimensional torus. in which you have these D-branes, which are suspended by the projection on sigma onto that that torus. That cuts away several regions in that three-dimensional space. So it's similar to the edges of the Brane tiling coming from the intersection of the NS5 brane with the two-dimensional torus. And each set of branes breaks some amount of supersymmetry, and you are left with a two-dimensional 0,2 theory. So, as I said, most of the non-trivial structure of what I want to discuss today of this brane brick model happens on a three-dimensional torus, and it can be visualized by what's called the Coamoeba projection, the projection of that surface on those arguments of the complex variables. And furthermore, by what I would call a tropical limit of it, in which I just consider the skeleton of the brane brick model. This object fully encodes the two-dimensional gauge theory, and it's, as I will show you, it's a graph that is dual to the periodic quiver that describes this gauge theory. So this is a periodic quiver for one of the two-dimensional theories under consideration. I'm not showing what the unit cell is. If the unit cell only contains one node, this would be the periodic quiver for C4. The periodic quiver, the gauge theory for C4 is just the dimensional reduction to two dimensions of n equals to 4 super Young Mills. We know it very well. It has A, X supersymmetry, and it has 4 chiral fields and 3 Fermi fields in the adjoint representation. Here you see that at each node you have 8 arrows coming out. They represent the 4 chiral fields, depending on how you connect to other things. And you have 6 red lines, which corresponds to the Fermi fields, that correspond to these 3 adjoint Fermi fields that I was talking about. The dual object, which is the skeleton of this brane brick model, is what I represent here. And you have to think about it as a brane configuration. So you have to figure inside of each of these 3-dimensional bricks or balls, you have D4 branes that corresponds to the gauge groups. That this tessellated surface is just, as I said, a limit of the actual sigma intersecting this 3-dimensional torus. And when 2 of these objects, these bricks, come together, you will have some matter, and those intersections can be oriented, and those will correspond to chiral fields, or can be unoriented, and those correspond to the Fermi fields. Unoriented because, well, the fact that they are unoriented is nice because the theory, these two-dimensional theories are invariant under the exchange of the Fermis and the conjugate Fermis. And furthermore, the edges of this construction, in which you have a Fermi and a bunch of chiral fields or faces that look like the pages of a book, corresponds to a J or E term for the gauge theory. J or E term is the analog of F terms for two-dimensional 0,2 theories. Okay, so you see the additional structure. So first of all, you see that this is not random. This encodes not only the quiver for the theory, but also the J and E terms of the theory. It follows from geometry, and there will be some nice connection to geometry from the combinatorics of this object. And you see other things like that, I would normally include in a talk about brane brick models, but I think that I gave one about it in this meeting long ago. You see, for example, that that the Fermis are square faces, which means that every Fermi participates in 2 J terms and two J. The J terms of every Fermi are given by the sum of 2 monomials, and similarly, there are 2 monomials in every E term. Okay, this is very specific of toric theories or theories associated to toric geometries, and that's what allows this combinatorial structures to arise out of these gauge theories. So it's very special. They're not generic two-dimensional theories. They're very special two-dimensional theories that have not only certain amount of supersymmetry, but they have certain structure in their J and E terms. And this is very similar to, let's say, the dimer model or Brane tiling being bipartite. So it's the analog of that property.
So this three-dimensional shape is the truncated octahedron?
Yes.
And what type of other shapes in general can you allow?
Oh, you can have all types of shapes. You know, there are cylinders, like octagonal cylinders, and many cubes, things like that. The truncated octahedron is a very nice one because it's the three-dimensional permutahedron, right? So it's the analog of the hexagon. The hexagon is the two-dimensional permutahedron. The segment in the Hanani-Witten kind of configuration is the one-dimensional permutahedron. So this is generalizes to higher dimension, if you want to.
What would be in general dimension?
Well, it's the n dimension. So the Cn theory, corresponds to the n-dimensional. So for n plus 2, Cn plus 2 dimensions, it corresponds to the it's the n plus 1 dimensional permutahedron, something like that. It's the corresponding permutahedron.
So there is a notion of a permutahedron for n dimensions.
Yes, and you can find them in Wikipedia, and it has some nice properties. Yes.
And what in 2 dimensions, we saw that most of the models are mixes of hexagons and squares. So the squares will be the conifold, the hexagons would be the C3, and everything else is in between somewhat. What would you say over here?
Right. So what you say is that so there are families that I know very well that are mixtures of squares and hexagons, and that you say something more that that probably for every toric geometry there is a phase which is realizable by squares and hexagons. Right. The analog of that result, I don't know. That's a very interesting question.
See. Okay. Okay. Thank you.
So these geometries, I mean, it's not that we are interested in drawing complicated figures. No, once we know how to do them, we are interested in drawing complicated figures. But these objects, very much like Brane tilings, simplify the connection between gauge theory and geometry. If you give me the geometry, they simplify the identification of a gauge theory on a D1 Brane probing that geometry. And on the other hand, if you have one of these theories that belong to these families that come from this kind of construction, it simplifies the determination of the corresponding geometry. And as usual, these are things that, as I always tell my students, that you don't appreciate until you suffer them, right? So unless you have tried to do this connection, you might think that it's straightforward. So again, every brick in this construction corresponds to a gauge group. Every oriented phase is these things that I'm representing in black corresponds to a chiral field, two-dimensional chiral field. An oriented square phase corresponds to a Fermi, and the edges of this construction corresponds to some gauge invariant term, which I will call a plaquette, that encodes a J or E term monomial. And there are some consistency conditions that these objects satisfy. They're not random objects of this type. There is anomaly consideration, the stress condition that you can build in the construction, and so on. So let me tell you the simplest example now, which I already showed you, but let's discuss it in more detail. It's C4. This is the toric diagram. It's just the minimal tetrahedron in 3 dimensions. The gauge theory is the one that I discussed before. It's just one gauge group with 3 adjoint Fermis and 4 adjoint chirals. You can think about this as the dimensional reduction of n equals to 4 super Young Mills. Every one of the 3 4-dimensional chiral fields becomes a chiral Fermi pair, and then the vector multiplied in 4 dimensions becomes the vector multiplied in 2 dimensions plus an additional adjoint chiral. So this is what it is here. And the JID terms are given here. You can think about these ones as coming from the 4-dimensional superpotential. And you can think about these other ones, which contain the new chiral field, which I call W, as coming from the D terms in 4 dimensions. So what I would say is for every Fermi, which is here called lambda 1, lambda 2, and lambda 3, you have a J term which consists of the difference between 2 monomials, and an E term which is the difference between 2 monomials. This corresponds to these edges on these squares that we were talking about. I will later flavor this quiver. I will add one additional chiral field by adding, let's say, some D8 Brane. And this field doesn't appear in any of these J and E terms because there's no gauge invariant that you can form with it. Okay, so the periodic quiver was like this. By the way, this cube is just there to give you a sense that this lives on a 3-dimensional torus. Of course, this is not the unit cell because it contains more than 1 point. It has 2 nodes there. You see that there are 4 chirals that are pointing in different directions, and the 3 Fermis. And this is the dual Brane brick model. It's obtained from this by graphical dualization. Most of the time, I will be thinking about the universal cover of these things. So not just on T2, but on R3, not just on T3, but on R3. I will also talk about these 3 dimensions as the quiver space. At some point, I will say, okay, there's this XYZ that corresponds to quiver space. Questions so far? Oh, good. Okay, so let me tell you a little bit about the combinatorics of these objects. As I said, the J and E terms of this theory is coming from Toric Calabi-Yau fourfolds are very special, has a very special structure, which is reminiscent of the toric condition for Brane tilings, which is that for every Fermi, for every conjugate Fermi, if you want, the J terms, which are things that have to vanish because they're equal to, they're equivalent or analogous to F terms in 4 dimensions, are a difference of 2 terms. These 2 terms here, J plus, J minus, means a monomial in chiral fields. So there's one with the plus, one with the minus, the same thing for the E terms. And you can combine these J terms with lambda and form the gauge invariant, or you can combine these E terms with the conjugate Fermi and make a gauge invariant. So sometimes we talk about the plaquettes, which are these combinations, the product of the Fermi with the J term. It's a closed loop in the quiver. There's another closed loop in the quiver, and these ones are closed loop in the quivers that go through the Fermis in opposite direction. So you can think about them as using the conjugate Fermi. So a central thing that I will use it's the notion of a brick matching. You can call it generalized perfect matching or just perfect matching. It's the analog of the perfect matching in this setup, and we have different definitions of it. So let me tell you a few of them because they are going to be useful in different ways, okay, at different times. So the first definition, which is the first one that we introduced in our initial paper, is that a brick matching is a collection of Fermis and chiral fields, and also you can think about conjugate Fermis, such that every packet here is covered exactly once in the following way. So either you have chiral fields in this collection of fields that exactly cover the 2 J-term plaquettes of a given Fermi, and if that happens, then or it's either that or it just covers the 2 E-terms plaquettes. And depending on which of the 2 the fields in the brick matching covers, then you add either the Fermi or the conjugate Fermi. So meaning if you didn't cover the plaquettes for the etherns with chirals, you add the conjugate Fermi that was part of that plaquette. Or if you didn't cover the plaquettes for the J-terms with the chirals, you add the Fermi field. Sorry, I might miss I don't see the conjugation, but you add the other one. Okay, so you add the other one. And again, this also has generalizations to higher dimensions. So that was the combinatorial definition, and it's a combinatorial definition that will enter when you compute the moduli space of these theories. It will be relevant to cover all these J and items. Okay, there's a definition, the second definition that was realized by Kenyon, which is a little bit anticlimactic definition, which is that the definition of the perfect matching is literally the same definition of the brick matching is literally the same definition of the perfect matching. If you think a little bit, I never emphasized the role of the vertices of the zero-dimensional objects, the corners of the Brane brick model. I never assigned any gauge theory interpretation to them, but it so happens that the perfect matches are such that when you think about the chiral fields in them, and the Fermi fields can be inferred by the chiral fields in the perfect matching, every vertex in that three-dimensional lattice is covered exactly once. There is a third definition that we introduced before this one, and it's equivalent to this one with Asim Hassan, which is that once you have for every Fermi, you can create four close chiral operators, okay, that are close in the quiver, four mesons, which is just take the J and you multiply by E. Remember, J had two terms, E has two terms, then you have four possible combinations, right? You already see that this is smelling like the four corners of the corresponding Fermi face, and it's exactly that. And with using these chiral cycles, we call them chiral cycles, you can define in a third way the perfect matches, is that the chiral field content of a brick matching is such that it contains, it covers every chiral cycle exactly once. So you have this bunch of closed loops, 4 times the number of Fermis. Actually, they are repeated. They will appear in a repeated way because there will be Fermis that share corners. The perfect matching is a collection of the chiral fields such that every one of these cycles is covered exactly once. Okay, very similar to Brane tilings. And furthermore, as I mentioned, these two definitions are really equivalent. You can map the vertices of the Brane brick model to the chiral cycles. So this one is, I would say, the most natural one. This will become important for us. I mean, there's many natural things that we would like to say about this crystal melting model that to me only come natural when thinking about, you can only show them if you think about these brick matches in this way. So I haven't done it yet. I would normally do it at this point before this, but I will show you that there's a very natural map between brick matching variables and chiral fields in the quiver. So you can think about a chiral field, or it's useful to think about each chiral field as made out of out of brick matching. The same thing that we do for Brane tilings. Once you take that definition or that map into account, it will turn out that all chiral cycles are not only equal, but they're equal to the product of all brick matches. This is very similar to what some people might be familiar with, that every term in the superpotential is the product of all perfect matches in Brane tilings. So it happens the same. So what you can say is that, modulo J and E terms, you know that all chiral cycles are equal. Modulo J and E terms, all these chiral cycles are going to be equal. And this follows from the combinatorics plus the maps that I'm going to introduce in the next slide. So this is something that you know. Okay, very good.
Yeah, I'm sorry. Hi, Sebastian. So
Yes,
one
hi.
comment here. So the
Yes.
vertex is corresponding to the trace condition of the 0,2 supersymmetry, right?
So, well, very good. So, as we wrote in the paper that we wrote together,
Yeah,
if
right.
you want to automatically implement the trace condition, you have to, these things have to glue in certain ways along the vertices. What's going to happen
Yes.
is that when you look at the trace condition, which is a sum of these products over all the Fermis in the theory, the chiral cycles will appear in pairs with opposite signs, which is the fact that every vertex is going to be shared by two Fermis.
I see.
I mean, this was observed before, and it's implicit in or explicit in what we did, but that's how these things appear there. Yeah.
I see. Okay, great. Thanks.
Very good. So why do I like this? Why do I say that this simplifies the connection to geometry? Is that the probe geometry, if I give you the gauge theory, is corresponds to the classical moduli space of the gauge theory, which corresponds to imposing vanishing J and E terms and also vanishing D terms. And we can, just apply this method, and we do it all the time. And at some point, it becomes pretty complicated. Well, it's simple in principle, numerically more involved. But okay, this is the combinatorics of J and E terms. So let me tell you a little bit about that. What I want to advocate is that there is, if you think about every chiral field, and I will call Xi the chiral field in the theory, as a product of the perfect matches that contain that chiral field, then you automatically solve the vanishing J and E terms. And that automatically solving J and E terms is a consequence of the definition of the Brane matches. Okay, something that was very simple to prove for Brane tilings. It's similarly easy in this case. So here, this P, this exponent is either 1 or 0, depending on whether the perfect matching contains the chiral. So we're just saying, think about the chiral field as a product of perfect matches. I mean, this is the common thing. Typically, we are inclined naively to think, and it's useful in some context to think about a perfect matching as a collection of chiral fields. But for these purposes, the right way of thinking is that a perfect matching is made out of all the perfect matchings that contain it. Okay, that's the other way. So once you do that, these Brane matches automatically solve all the J and E terms, so they bypass this part of the calculation of the geometry. And actually, you can think about these Brane matches as the GLSM fields that describe this Toric geometry. There will be one Brane matching for every point there, or a collection of Brane matchings for every point in the Toric diagram. This is a three-dimensional Toric diagram for the Calabi-Yau 4-4. Very good. So let me show you the ones for C4. I will discuss C4. The ones for C4 are very simple because C4 only has the X, Y, C, and W chiral fields, and they are equal to the perfect matches. There's one of these examples in which the perfect matches just coincide with the fields in the theory. Similar to C3, similar to the conifold. So here I just represent, just for you to start seeing, I just shade the face that corresponds to the X, Y, C, or W field. And furthermore, we can associate them to different points in the Toric diagram, right? So there will be one of the corners of the Toric diagram that corresponds to PX, another one that corresponds to PY, and so on. Questions? Good. Okay. So what the idea? I talked about Brane models. I told you there are some combinatorial aspects that are going to be important. One of them is the notion of Brane matchings. And the second thing that is important is the fact that differences of Brane matchings lead to oriented surfaces on the Brane brick model. So the difference between any of these two brick matchings results in an oriented surface or a disjoint union of oriented surfaces on the Brane brick model or in its universal cover. So at some points I will be talking about perfect matchings of the original theory. Like in the previous case, there were only four because I was talking about the Brane brick model on a torus. Of course, at some point I will like to talk about the covering space. So I'm allowed to talk about many more different brick matchings there, analog to the perfect matchings of the hexagonal lattice that I showed in my first slide. So these things now can combine in many different ways. So these things define our oriented set. What do I mean by the difference? I mean that the faces of the chiral fields that are in the subtracted brick matching are, you flip its orientation, and whenever some field is contained both in the initial and in the final, in one and in the second perfect brick matching, then they are deleted. So that's what the surfaces are. And let me tell you about two instances in which these surfaces will be relevant for us. The first one is what we call phase boundaries, which are the analogs of the zigzag paths for Brane tilings. Okay. So they're in one-to-one correspondence with the edges of the toric diagram, and they're given by the difference between the corresponding perfect matchings at the ends of that edge, right? So you take this perfect matching minus this perfect matching, it gives you a surface on the torus with some homology that is given by the difference between these numbers, which is very similar to zigzag paths. And here, if I color every edge, every one of these 6 edges, you will have things that wrap in different ways along T3. Some things that wrap around X, and so on. And let me give you an example how this actually looks in the Brane brick model. These were PY and PW. The difference between two, if you think about them in the covering space, will look like a surface. And I represented a piece of the surface. Okay? And if I represent the unit cell, which is not this thing and it's not this cube, it will have the appropriate winding numbers. Questions? Okay. And the other way,
sorry,
which
can you show the picture again of before?
Yes.
So the thing that's now colored, that's what corresponds to the zigzag path in the Brane tiling.
The thing that is colored is the zigzag path.
Or this is okay. And yes. Does it like go around the nodes like in the Brane tiling, or is it
right?
Because it looks
right.
like
so,
you've just colored the surfaces.
So we don't have a local definition of the best definition that we have of these things is difference of these corner perfect matchings. We don't have a local definition of this thing. I think that the closest that we have to the local definition is that this corresponds to anomaly-free global U1 symmetries. So so you will see that these things do the right thing on the faces. But we don't have a prescription that, wrap it in this with this concavity and then with this. That would be something that I think should be there, but I don't know.
Okay, thank you.
Yes, and you also see that untwisting wouldn't work in the way that one think it would work because the anomaly cancellation for the gauge symmetries and the global symmetries are different. So the counting is different. So this cannot be untwisted to something that we'll call a brick. Yeah. Okay, so another place where this is where I will use this surface come from differences of brick matches is to define a height function, which it's a key ingredient in building these crystal models. And for every perfect matching, you can define an integer value height function, either on Quiver space. It's a function of the coordinates of this three-dimensional space where the Brane brick model lives or where the periodic quiver lives. And to do so, what you have to do is you have to introduce some reference perfect matching. And then you have to take the difference that you will use to determine the height functions for every perfect matching, every brick matching. And you take the difference between these two. This will give you a collection of oriented surfaces. And you will define, you will pick what the height function is at a given point. And then this will be a convention for you. This is an arbitrary choice. And then every time you cross one of these surfaces, you increase or decrease the height function by 1, depending on the direction of the crossing. And the direction of the crossing is the direction of the chirals in the surface. So if the surfaces are pointing in this direction, okay, you say, okay, I will increase the height or decrease the height by 1 or by +1 or by -1. There you go. So that's the definition of the height function. Of course, if you live in a three-dimensional torus, it's not, this is not well defined, right? It's not single valued, and we are more used to what's called the slope of the height function, which is how much the height function jumps between when you go between equivalent points in consecutive unit cells in the 3 dimensions. We do the same for the Brane tilings, and this is one efficient way, for example, to find the positions in the toric diagram of the corresponding brick matches, if you want. This is one of them. So, what is the crystal model that I want to talk about? I want to first define it in terms of the periodic quiver. So, let me define it for you. Let me see. Okay, very good. So, and I will talk about this initial quiver that I talked to you about C4 with an additional flavor. So this is the quiver I will consider. So I will consider the universal cover of the quiver. This will be 3 of my 4 dimensions. I will call it this universal cover Q tilde. And the corresponding 3-dimensional space, the coordinates there, X, Y, and Z. There is one type of atom in this crystal because there's a single type of node in this quiver. And I will define the crystal or the frozen crystal or the crystal before melting as follows. I will assume that this flavor appears in one of these points. It's connected to one of these points in the universal cover of the quiver. It's setting an origin for the crystal, if you want, some special node. And then there will be one atom in my crystal for every oriented path of chiral fields starting with Q, modulo J and E terms, right? So I will look at paths of chirals that start from Q. I will consider them modulo J and E term relations, which deform these paths and make several paths that have the same endpoints equivalent. And this will be the atoms of my crystal. Okay. This is a 4-dimensional crystal, so I have to talk about what is the 4th dimension. So these atoms will have these 3 dimensions of the quiver space, but they will have a 4th coordinate that I will define now. So these atoms will be sitting on top of this periodic quiver. So what is the 4th dimension? I will call this special atom that is connected to this flavor the tip of the crystal. The 4th dimension, I will refer to it as the depth. We can call it height function, but since everything is going to be deeper than the tip, I call it depth. And you can think about that as the R charge of the operators, okay? Properly normalized. In particular, what matters here is that the chiral fields determine, regardless of what the actual value of the R charge is, they define a relation of overlapping. So if you have 2 atoms that are connected by a chiral field, then the one at the tail of the chiral field is above the one at the head of the chiral field. So the chiral fields define some overlapping relation. In the case of C4, it's very natural to assign, depth 1 to every time that you have one of the chiral fields, because they're all equivalent, and that's a very nice normalization that allows you to count, layers of atoms in a very natural way. So, if you think a little bit more about these atoms, every atom will be given by an expression of the following form. So modulo J and E terms, it will be defined by a path that connects this special point where this single flavor is sitting to some other node in the quiver, and the universal cover of the quiver. And you can always decompose that into the shortest path between I0 and J, and then a bunch of chiral cycles, maybe there's 0 chiral cycles, maybe there are additional chiral cycles. Remember, these are closed loops in the quiver. So these are loops that take you to the same point in 3 dimensions, but they add 4 fields, so it brings you down in depth. So you can think about, the first factor as defining the surface of the top layer of the crystal, and these additional powers of omega give you additional, it tells you that if you're omega to the nth, you're n levels below, you have an atom that is n levels below the top layer. And by the way, here the definition of what, for this to be true, we have used the fact that we have expressed our perfect matches in terms of chiral cycles, and that map told us that all chiral cycles are equivalent and are equal to the same number. So we can set all of them equal to some single variable that is what I call omega. It doesn't matter which one of these chiral cycles I'm using, this is true. Okay. Questions? Comments? Okay, very good. So this defines a crystal. Now let's try to melt it. I will talk about molten crystals. I will talk about 2 things. Something I will call I mu, which is the crystal itself, either molten, meaning with some removed atoms, or the original ones. And I will talk about omega mu as the set of the removed atoms. Now, depending on the slide, I will refer as melting configurations as any of the 2. Okay, so I might mix the 2, but it would be very clear whether I'm talking to the underlying crystal with removed atoms or the atoms that were removed. You can define the path algebra with the chiral fields, and you can mod it out by J and E terms. There's a melting rule that tells you what you can do, which says that if you have an atom in the molten configuration, or that has been removed, if you have an atom that has been removed that is given by this expression, some combination of 2 paths for some path that is in this, factor algebra, if you want, then the shorter path, the shorter atom, also has to be removed. Okay, this is simply given that if you want to remove an atom, you better remove all the atoms that were overlapping it. These atoms might not be exactly on top of it, they may be somewhere else, but they're connected by this path of relations that tells you that all these things are removed. You cannot remove them without removing the one that is on top. Okay, and I will show you an example. So, the first path defines the first atom. The second one, which is the shortest, is a shorter path that is missing this additional excursion into the crystal. It's clearly an atom that was above the first one, so it has to be removed if the other atom is removed. This is called the melting rule. Okay, and the molten crystal defines an ideal of A by the contraposition, by thinking about the melting rule in a slightly different way. So let me tell you a little bit about this height. So we talk about this depth, but there's something else that is convenient to define. I will call it the melting height, which is defined as follows, right? For every crystal, so let me consider two crystals. Let me call it zero is the frozen crystal, the initial crystal, and mu corresponds to some molten crystal. For every point, I will look at the depth of the top layer, and I will look at the difference between these things in the unmolten and the molten crystal. What is this measuring? Is measuring the height of the atoms that I removed. So you can actually normalize this melting height in such a way that it really counts the number of removed atoms for a given three-dimensional position. And it's also useful to define some partition function that counts the number of melting configurations with a given number of atoms. And hopefully that's not a fire alarm. I mean, it sounds like there's a fire alarm in my office, but okay. So
we can't hear it. It's filtered by Zoom.
It's very good.
Okay, I hope there's no fire.
Right. So let me talk about the crystal in more detail. So here is the periodic quiver for C4. Once again, each of these vectors, X, Y, C, and W, chiral fields, you can associate to some very nice vector. And the position in quiver space of a given atom is given, every atom will be given by a combinations of X, Y, and C and W fields. How many of them? An X, and Y, and C, and an W, all of them positive. And by combining these vectors, you get the position of this atom in 4 dimensions, in 3 dimensions. So this is, what about the depth? I will normalize the thing. I will normalize the R charge such that the depth is just given by the sum of the number of X, Y, C, and W fields. So the depth is the 4th dimension in this very special case, since every chiral field is equivalent in C4, it's just given by counting the number of fields. Of course, in more complicated examples, it will be different than this. So how do you visualize something that is 4-dimensional? I don't have such an imagination. So the first thing is you slice it at different values of the depth or the height, and you have these 3-dimensional slices at each value of the height. That's one possibility of doing it. And you can do that for both the molten crystal and unmolten crystal. So let me show you how it looks for the crystal that I was just talking about. The C4 crystal. C4 crystal means the single D8 brane there. And I give you a few layers up to depth 4. You have the tip of the crystal. Then at depth 1, you have obviously 4 atoms because you can reach them by using any of the 4 chiral fields. And then things become more involved, and these regions grow, these slices grow. And it's an infinite crystal. Here you see that the first overlapping atom in the 3 dimensions of the quiver appear at depth 4. So until this point, all these atoms have different values of X, Y, and C. You might or might not be able to see that from the picture. Once you reach depth 4, you have a combination of X, Y, C, and W that is a chiral cycle and allows you to reach exactly the same point that is here in 3 dimensions. So this is an atom that is literally below this one in 4 dimensions. Very good. And the other thing that you can see is that these slices seem to be tetrahedral, which seems to be similar to the shape of the toric diagram. This is going to be true. Again, we can count how many atoms are at each level, and furthermore, we can generalize this for crystals based on the generalizations of Brane models to higher dimensions too. So we can do that also more generally. So in order to connect things to Brane models, it is convenient to define the top layer or the surface of a crystal. So if I have a crystal I mu, I will define the surfaces mu as the collection of atoms that are at the minimum depth for each value of x, y, and z. Literally the top layer. By the definition that we have before, if you can realize that if you consider those atoms alone, the top layer of your crystal, which is 4-dimensional, very difficult to visualize, and you consider the chiral fields connecting all of them, you cannot form a closed loop. Why not? Because if you form a closed loop, that will correspond to an atom that is in the same position at the deep and a larger depth, so it would not correspond to an atom on the surface of it. Okay. So let me show you the surface of that, the unmolten C4 crystal. So here I'm just giving you depth 1, depth 0, 1, 2, 3, 4, 5, 6, and 7. So the things that are on each column differ in depth by 4, which I told you is, in this case, is what you need in order to form a closed loop. And, you know, so far until you reach this point, until depth 3, every atom is on the surface. However, once you reach depth 4, this is an atom which coincides with the atom that was there before at depth 0 that is not on the surface. This atom is below, so you have to remove it. And you can see that the similar thing happens at higher depth. Every time that you increase by 4, you have to remove the atoms in the previous layers. So whenever d prime minus d is 0 mod 4, you have to remove the atoms in previous layers. So this is how the surface of this crystal looks like if you want to visualize it. So we can already see that, you know, this tetrahedron that I get in a slice looks similar to the tetrahedron of the toric diagram, at least in this example. The connection will be more clear later, but even at this level, it's more or less clear why. You know, these vertices corresponds to the ways in which you can maximize your distance to the origin at a given depth. And the way to maximize the distance to the origin from the origin at a given depth is by using all collinear vectors, meaning using a single type of chiral field. And remember that in C4, every corner corresponds to a brick matching that corresponds to a single type of chiral field. So it's not surprising that we see these corners that are very much like the corners here. You know, the path that takes us to this atom is literally a collection of only X fields, only Y fields, only Z fields, and so on. The other thing that I want to mention is it's nice to think about solid partitions. If you ever counted solid partitions, the counting looks like this. There's no analog or there's a proposal that is similar to McMahon function to count these things, and it doesn't work. I think at depth 6, it fails. So we are trying to connect to this kind of partition functions. So another way of thinking, so I gave you one way of visualizing this crystal, which is this slicing. Another way of visualizing crystals is by Hasse diagrams, right? Because you know, the relation of being overlapping with other atoms defines a poset. You know what is on top of each other, depending on where they're connected by chiral fields. So you can organize these things in terms of a Hasse diagram. So here is again all the atoms in my crystal until depth up to depth 3. I also give you what the position is in 3 dimensions. I don't need to represent them in fancy ways. Here I can just put them at the depth that they have to be. And I have given different colors depending on whether atoms are connected by X, Y, Z, or W. So you see, first of all, that for every atom you have 4 arrows emanating from it, because these are the 4 chiral fields that you can use at each node of the quiver. And there are some atoms that from above are reached by many arrows, and there are some atoms that are only reached by 1 arrow. For example, this atom here is one that appears in one of these vertices of the tetrahedral slices, because it can only be reached by using fields of the same type, n times. So how does the melting rule appears here? Imagine I want to remove this atom, right? Of course, there are many configurations that have this atom removing it, but let's look at the minimal configuration that has this removed atom. And one way to do it, you have to remove, well, you have to remove everything that is on top of it. In this case, there's these 3 atoms, and then everything that is on top of them, and then everything that is on top of that. Okay, so the minimal way in which you can remove this atom is by removing all the ones that are on top of it. And you don't have to be thinking 3 dimensions, 4 dimensions. That's very simple, right? In particular, this kind of things is very easy to count melting configurations. So imagine that I say, okay, let me find all the possible melting configurations with 4 atoms, removing 4 atoms from this, and they have these different structures. You can count them. It gives you 26. This is the 26 of the previous slide. These are the solid partitions with 4 boxes. And you can count how many of them are with 5 atoms. Now, it's a very simple way of counting them. There are 59 of them. Again, this is the solid partitions. You can also think about the configuration with overlapping atoms. I'm going to come back to it later. I told you about this configuration when the first overlapping atom appear. What happens? How can I remove that overlapping atom? You can only remove that overlapping atom if that atom that is at the 0, 0, 0 in 3 dimensions if you remove 16 atoms. You can think about these 16 atoms like this. It's either by these different layers of at different depths, which are this layer 1 atom, 4 atoms, 6 atoms, 4 atoms, and 1 atom, or you can project everything to 3 dimensions, and you can say the atom in the middle has a different depth. It's a melting height too. Okay. Any question?
Yeah, how does it compare with the computation of Suresh?
Suresh, I'm not familiar with that, but how did it work? How was it? Sorry?
He did the computations of 4-dimensional partitions.
Right. So these things are there, and these things are complicated. I mean, what you will see in my conclusions is that I would like to get these things recursively, not by counting them like this. So, and that's where I think that the input from physics comes.
So then it would be nice to talk to him.
Okay, good.
I see. Okay, I need to check how did he use it. Govinda Jan, you may have seen him before, but he's in Chennai.
Right, I know that there's some upper bound, that like some limit that people have have calculated, and it's not extraordinarily high. But in the conclusions, you will see where I'm trying to. What would be my dream? What would be my dream? Right.
Okay.
So.
Quick question, Seba.
Yes.
Since we still talk, how much time do you think you need going forward?
30 minutes, 20 minutes, 10 minutes, 5 minutes. I don't know.
Well, okay. Let's see how it goes. Okay.
Yeah.
We've reached the hour mark.
Yeah. I know.
Okay.
So,
good.
Yeah. I can remain with whoever is here. Yeah, I already saw you packing, so it's fine. Don't worry. So
no. I was getting out my charger.
Yeah. Anyhow, don't worry. You don't hurt my feelings. Don't worry. So I already described or defined the model for you in terms of periodic quivers. I would like now to define it in terms of Brigg matches, right? So I want to show you how in Brane Brigg models, how the Brigg matchings captures all this construction. Visualizing these things in 4 dimensions is very difficult, so let me just refresh your mind and tell you how these things work in brane tiles, right? So let's consider D6 and D0 branes on C3. C3 has this hexagonal lattice dimer model, has 3 perfect matchings, very similar to what we have discussed before, one from X, one from Y, one for C field. And you can think about the PQ web, which is dual to this toric diagram, and the node that corresponds, the the point in the toric diagram corresponds to this perfect matching is in this region in the PQ wave. Second one is here, and the third one is here, and so on. Okay. So, how do we talk about the unmelted crystal? The frozen thing that we're going to start melting afterwards is defined by a perfect matching, and we call it the canonical perfect matching. And I will define for you later, but you can imagine that this thing with an appropriate choice of reference perfect matching to describe all the heights is going to give me this empty corner three-dimensional configuration that I'm looking at, that I'm interested in. And more or less you see it here. This looks like a wall, another wall, and the intersections between the walls. This is, of course, an infinite perfect matching. And in each of these regions, there are three regions in which the perfect matching coincides with the perfect matching of one of the corners of the toric diagram. Remember, it's the perfect matching of the universal cover. And then when they merge, when they come together, there are combinations of them. And you can kind of see the PQ web of the geometry already here. So you can see some discretized version of the toric geometry realized in the crystal. So what about the depth? The third dimension? The third dimension is the height function, which is defined by taking the difference between the perfect matching that you are interested in and a reference perfect matching. And then every time you cross one of these curves, you jump the height by 1 or -1, depending on the orientation. So it's very well known. So let's imagine I have this canonical perfect matching, meaning the unmolten crystal. This is going to be the reference perfect matching that I will use from now on. It's more or less the complement of this perfect matching. And when I compute the difference, I define all this set of curves, of closed curves, that you can think about them as the contour lines of the height function. And then you can paint it there, and you see what is the height. So the way in which I'm defining the height here is not in this three-dimensional X, Y, Z kind of way of the corner. Is I'm looking at, I don't know, 45 from the 1, 1, 1 vector from the corner of this room corner, and the height coming out of it. And this is what it is. This is the unmolten crystal. But then I want to think about melting configurations, and there are other perfect matchings. So I pick the first reference and I consider other perfect matchings, and I will get a set of curves. I can compute the height function. I can state it at infinity if you want, and it will look like this. So you see now that there's some difference with the previous picture. There's some things that have been removed, right? Something disappeared here. We have something at depth 0 that was sitting there. There was something on this edge that is not there. Something has been removed. The depth is not the ideal for me way of thinking about this thing. It's much nicer to think about this melting height, the height of what you remove. And you define it as the difference between the depths of the surface of the original crystal and the surface of the molten crystal. And it's much easier because you have P minus PR, and then you have P0 minus PR, and you have to subtract the two. So this is independent of the reference perfect matching. So it's even better. And in this case, what you get, for example, for this example, is these two things. So you see that you just remove two atoms from going to one crystal to the other, which were the two atoms that were sitting there. This is much easier to visualize. And it corresponds to these melting configurations, omega mu, that I was talking about. Okay? So how do you do this in terms of Brane-Brick models? The first thing that you have to do is you have to think about the Calabi-Yau crystal and the melting configurations in terms of big brick matches. And it turns out that there is a one-to-one correspondence between crystals and brick matches, or molten melting configurations and perfect matches, if you want. And it goes as follows. Well, I will do that. I will do that later. But now let me show you what the canonical perfect matching that describes the unmolten crystal is for C4. Right? It looks like this. Right? This is the empty corner configuration. So in the empty corner configuration, you have 4 regions. One of them you don't see it, it's behind. These 4 regions correspond. Inside each region, the perfect matching looks like one of the 4 corners of the toric diagram. Then there are regions where these things come together. pairwise they come together in 6 regions, which correspond to the 6 edges of the toric diagram. And it looks like something like a PQR web, if you want. It's some generalization of the PQ web. So there's some discretized version of the toric geometry here too. Very interesting if you look at it, at this thing from, let's say, exactly one of the directions of a single type of chiral field, you get something that looks, in which these truncated octahedra look like hexagons, and this looks like the perfect matchings defining the 3-dimensional empty corner, not surprisingly. And if you look at it from exactly the opposite direction, the Brane tile, the perfect matching, this canonical perfect match is made out of just one type of perfect matching, the one that corresponds to that direction. This has to do with the chiral fields given a discretized version of the height function, of the gradient of the height function. Very good. So how do we go from a crystal to a perfect matching? We do something that Sendroy did many years ago, and then Oguri and Yamasaki also wrote about, but I think that Sendroy is already clear what to do. You imagine that I want to go from a crystal to a brick matching. So what I have to do is I have to consider the top layer of the crystal, and I project it into the 3 dimensions of the Quiver space. After all, this is the top surface, so there's no additional dimension. And I conceal the chiral fields that connect the atoms in that top layer. And I already told you that those chiral fields don't form loops. Because of this property, the complement of this thing is a perfect matching. It's a brick match. And the same can be done, and the same is done for Brane tiles. You know, if you think how does someone go from this 3-dimensional crystal to a perfect matching, what you do is you take the surface, you look at the chiral fields connecting the atoms in the surface, you project them to 2 dimensions, and then you look at the complement of that. These are the fields that you need to remove in order to remove the loops, and it's a perfect matching. Yes, Sami.
Can you think of those arrows as baryons in the?
Yes. These are baryons. Yes, indeed. Yes.
So these are so you could still associate gauge invariance. So you just have a collection of baryons for each such.
So the crystal or the crystal is a collection of baryons, and it's on top of that you put the melting rule, which tells you how you can remove them. Right? You're going to remove collections of baryons. You're going to remove collections of atoms.
So that's like what would be the gauge 2 interpretation?
The gauge 2 interpretation that these things are invariant under the mesonics. These collections are invariant under the U1 cube mesonic global symmetry, and because you killed all the loops. These collections of things, you can call it the fixed point of the torus action and so on.
I see. So, okay.
So, but it's a very good question. So if you look at the crystal for C4 and you do this exercise that I did, you get this thing. You know, this is the surface projected to 3 dimensions and the chiral fields in it. If you look at it, there's no closed loop in the arrows. This is not the periodic quiver that I showed you before. It's a piece of the periodic quiver that I showed you before. And these arrows go in the direction in which atoms are overlapping, so you can literally think about them as giving you the gradient at each point of the height function. Very good. And that's consistent with how our layers look like. Very good. So what is a melting configuration? And I'm just close to the end. Is some brick matching. So let me describe one of them. Okay. So a very interesting one that I wanted to come back was this configuration with 16 atoms that had 2 overlapping atoms in it. So these are just 16 atoms out of these atoms of this crystal for C4. It happens to have 2 atoms, one on top of each other in the 4th dimension. So these are all the atoms. If you project them to 3 dimensions, it looks something like this. Right? It looks like 15 points. with one of them having height 2. You can think about them in terms of the models, it looks like the same. And you can also see that this corresponds to a perfect matching. So here I'm taking the perfect matchings of C4, of the universal cover of C4. I taking the canonical one that represents the crystal without melting, and I taking another one which corresponds to this configuration. I slice things in half so you can see inside of this cluster of bricks, and I didn't tell you what these brick matches are outside of these regions. The two of them coincide outside of these regions, so they're going to cancel when I take the difference between them. But once you take the difference between these two things, it gives you a set of nested surfaces. There's one that is outside, and there's a second one that is inside. So once you think about the height function, you will recover the overlapping atoms from the height function. So this is just to say that all these things are described by brick matchings and the Brane brick model. So what is so I said everything for C4, but let me just say what is general about this construction. Our construction applies more generally. In particular, you can think about general Toric Calabi-Yau fourfolds. What do you do there? You have the underlying structure is given that the universal cover of the periodic quiver of that geometry. You will have many types of atoms now, as many as type of gauge groups. And you will also like to consider general flavor branes, right? General flavor branes are general configurations of flavors. You know, you can have different numbers of incoming chirals, outgoing chirals, and Fermis, and you have all kinds of interactions coupling the flavors to the fields in the original quiver. So here I call Q, Q tilde, and psi the flavor chirals and Fermis. O are some chiral operator inside the original quiver, or the D0 theory if you want. And capital Phi is a Fermi operator, which in principle can be made of one Fermi and several chirals in the original quiver. Okay, so you have all these kind of couplings. The type of brane that you like to consider will pick one specific types of couplings and flavors. And you will have, and you see you have how many top atoms? You have as many atoms as the incoming chirals. There will be NQ of them. And now you have additional relations coming from the Fermi flavors, 2 and F of them. So you can already imagine that there will be different behaviors depending on how these two numbers interplay. Whether NQ is larger than F, whether you have more top atoms than relations, whether you have more relations than atoms, or whether you have an equal number of atoms or related number of atoms and relations. So what can happen is that the crystals might be infinite, like the one I showed. There was no Fermi flavor in that case, no additional relation. They might be finite, or they might be infinite, but effectively lower dimensional, which is the same thing that we have seen in Calabi-Yau. Okay. And again, these things can lead to, as I said, different flavors can lead to different versions of this discretized Toric geometry. You can think about like in these discrete PQ waves of resolving geometry, like growing up some cycle and so on. All these things have representations in this kind of language. How do you determine the brick matching? You determine it in the same way that for the quantum configuration, the same way that I told you before. You look at the surface of the crystal configuration, and you can consider the complement, and you can write the partition function for these things. Okay, I'm not going to show you this example, but this is an example of a D6 brane in C4, right? You have seen many of these in some other papers. You have a quiver and a Fermi field now, and if you want to specify how that particular flavor brane is embedded, you have to give me what is the coupling to the fields in the D0 brane, which is this one. In this case, this coupling would kill any operator that has a Q and a W in it. So any atom that you would like to have a W in it is not there. So then when you slice your crystal, you will see that at each depth, yes, you have X, Y, Z, and W coordinates, but at each depth, the slices are really two-dimensional. So the crystal is really three-dimensional, which is what you expect. So what are the conclusions? So we introduce a statistical model of crystal melting for non-Toric Calabi-Yau fourfolds. We formulated them in terms of periodic quivers and Brane brick models. What are the future directions? There are many things that I think that are interesting. We are among friends, so it's okay to talk to you. I'm not going to scoop me without letting me know 24 hours in advance. So what are things that I haven't said this to many people, so it's fine. So what is interesting to do? First of all, investigate this generalization to Toric, this implementation that I already outlined for general Toric Calabi-Yau fourfolds and general Brane configurations in more detail. See if there is any subtlety there. Study the relations of between crystals that are related by triality, which are dual phases, where they capture the same geometry in the same way. More interestingly, once you do triality, which is the analog of cyberduality here, the flavors change. First of all, the entire quiver might change, but you might even arrive in the same quiver or arrive in the same quiver after a number of mutations, but the flavors change. So what it means is that you are evolving between crystals of different types, of different sizes and shapes. You might be growing some cycle in this resolved geometry, for example. And you might even be growing a finite crystal and making it larger. Why do I think this is interesting? Because, the dream would be to think about how these partition functions transform under triality, and if you understand that, to use them to, iteratively generate the partition functions, let's say for C4, out of nothing, right? You can do a similar game in the conifold, right? You can start from flavor conifold, and people always tell me that Sandroid did it. I don't know, but no, you can convince yourself that you can do it. You can start from the crystal for the conifold with a single atom and just do cyberduality, and you know how the partition function transforms. And what you're doing is you're growing an atom that looks more and more, you're growing a crystal that looks more and more like the resolved crystal for the conifold, the resolved PQ web for the conifold, which contains two factors of C3 in it. You can do that. You can do a nice change of variables that is very well inspired by how fractional branes work in this case, and you can take a square root and you can get the McMahon function to any order that you want. Okay, so you can just place, start with 1 plus a recurrence, tell Mathematica to do it to whatever order you want. You take a square root after the change of variable, and you get the plane partitions. I imagine, and that's one thing that I would like to do, and I'm trying to do. A similar thing in this case would be very interesting for many reasons. Already knowing this recurrence would tell you something very interesting that generalizes cluster algebras, but it's inspired by two-dimensional theory. Investigate the high temperature limit, see if it has anything to do with the mirror, and investigate whether something like Quiver Yangians that are based on these crystal models already, Galakov and Lee used the periodic quivers in their first papers. So that's another direction to investigate. So that's everything. Thank you.
Let's thank Seba. Do we have questions?
Yes, I have a question. So what is the temperature in the context of the PPS counting?
Right. No. Right. I don't know. Yes, I'm not familiar. In this case, would be look for the typical configuration when the number of atoms is very large. You can sample these things, and there are some way in which to define what is the typical one. Yeah, look at where that is approximated by a mirror or not. That's
Okay.
that's it. Yeah.
So a few weeks ago, we had a talk by Yinan here on putting M theory on toric CY4s. So the theories you obtain here, well, of course, you're studying WPS treatment, but the theories you obtain here, they should also tell us about these 3D English 2 theories we get from M theory on the Calabi-Yau force. Have you thought about this? I know it's not very relevant to what you've told
so
us.
about the 3D theories, no, I don't know. Yeah, I know. I have worked on them, but I haven't thought about what is the connection to these things. Yes.
Because of course, yeah, for these 3D theories, it's not just geometry alone, but it's actually a tough problem to figure out what will be the 3D theory. But,
right.
So maybe this can give some insights.
Right.
Okay.
Yeah.
I think so one relative comments. So the tricky point in Yinan et al.'s work is that because you only have 4 supercharge, so the modular space is not actually protected by enough supersymmetry. So we cannot be 100% really trust the result there.
Right.
But classically speaking, or if regardless of that thing, something might be the BPS quiver of those theories might correlate it with the Brane brick model quivers. Or those theories compactify on S1, then you have this extended BPS quivers, like might have something to do with this because you have similar correspondence in 45D, right? If you have Calabi-Yau threefold EM theory, then the BPS quiver on S1 is basically the same as the Brane tiling thing.
So instead of solving problems, you introduce new ones.
Yeah, right.
That's good, no?
It's
Maybe it's good.
I like the comment. I like it. Very good.
I mean, so you try
there are
to.
no answers. There are not even questions. Yes.
Yeah. So the BPS quiver. What would you like to do with the BPS quiver?
We see. That's my question. Can you do something?
Okay.
I've not looked at these theories, so I cannot say. That's why I asked.
Whatever you did before, you redo it again and again. If there were interesting things before, there will be similarly interesting things now. I guess.
Very good.
Since I didn't do that.
So do we have more questions for Seba? Okay, I would say let's thank you again.
See you. Bye-bye.
Thank you.
And we can stop the recording.